So I'm Joe Salisbury. Welcome this morning. Doug Vandermark, Chris Hunt, Jim Irish, Sean Shelado, and others at UNH are my collaborators. And we've got more collaborators too. A few of them I'll mention as we go along. So this talk today is called Factors Contributing to Variability in PCO2 and Calcite Mineral Saturation State in the Coastal Gulf of Maine. And I've made this talk pretty long, so I'm going to go pretty fast. We'll answer questions at the end. So I want to go over a little background again for those folks that tune in regularly. You've heard a lot of this. I'll try and be quick. Talk a little bit about why the coastal Gulf of Maine is particularly sensitive to ocean acidification. Show some vignettes from our observations in the Gulf of Maine, and also talk about factors that I think contribute to the observed variability of the carbonate system at decadal timescales, seasonal timescales, and even daily timescales. So some of these terms you've seen before. pH is a hydrogen ion concentration. pH is sensitive to temperature. When the temperature goes up, excuse me, the pH goes up. When the carbon dioxide goes up, the pH goes down. PCO2 is the partial pressure of carbon dioxide measured in microatmospheres, and its concentration divided by the solubility. And when the PCO2 goes up, the pH goes down. When the temperature goes up, assuming what we call isochemical conditions, the PCO2 also goes up. And in the western Gulf of Maine, and Helmuth showed this a couple presentations ago, pH is closely related to PCO2, and this is the same slide that Helmuth showed, and this is from two independent measurements, two independent instruments rather, at our at the Syracuse PMEL UNH carbon dioxide buoy, and this is a line, and we have a good relationship here, and thermodynamically it should be a bit of a curve, but even when you put a quadratic equation in there, it only explains about 1% more of the variability. So for this talk, think pH going up, PCO2 going up, pH going down, and vice versa. Okay, the saturation index, or omega, of the mineral aragonite is basically the product of the calcium concentration, the carbonate ion concentration, divided through by the solubility. And it's also affected, so of course, I think everybody on here knows that shelled organisms need calcium carbonate, or shelled organisms that use calcium carbonate would like this omega to be above 1. They have to work really hard if it gets near 1. And if it gets below 1, it becomes thermodynamically unstable, and these things could dissolve away or else be really stressed because they have to use a lot of energy. So this is affected by temperature, and sometimes this is an unappreciated fact. Temperature goes up, omega goes up, and it also varies with PCO2. PCO2 corresponds to omega. If it goes up, PCO2 goes up, omega goes down, again at a specific temperature, and it varies with pH as well. One thing that I wanted to note here is that this omega of 1.6 has been shown in the lab to be some kind of threshold for calcification of a couple of species that are of commercial importance, oysters and clams, at least in their larval stages. And so I want to show you in some of our data, keep that in mind, that 1.6 may be an index. Okay, so factors that make the Gulf of Maine, particularly coastal Gulf of Maine, particularly sensitive to acidification. It's cold, it's fresh. The fresh component is poorly buffered, and Alec Wang talked about this a few weeks ago and has written a little bit about it. And there's also strong seasonal productivity and mixed layer dynamics. All right, so it's cold. Relatively cold. So here's a little video clip from Department of Fisheries and Oceanography in Canada, and you can see this is the daily climatology here. And you can see, you kind of get the sense of a negative heat flux coming down from our neighbors to the north. And here in New Hampshire today, we have quite a negative heat flux from Canada in the atmosphere today. It was 26 below 0 Fahrenheit in central Maine last night. But you also see the seasonal progression of temperatures with relatively cool temperatures and a big seasonal range. And the seasonal range is larger near the coast. Okay, so this affects our carbonate system variability. So here is the similar model, or the same model output, that this time is tracking the climatology of fresh water. This is really important for the carbonate dynamics of our region. So there's quite a freshwater subsidy from the Scotian shelf up here where the mouse arrow is. And of course that works its way into the Gulf of Maine on a seasonal basis. And this is the majority of the freshwater flux to the Gulf of Maine. However, I want to note that right here on the coast, on the western coast, we have a local source of fresh water that reaches its maximum in the summer months, in the early summer months, in the late spring, early summer months, when these commercially important shellfish are spawning. And a note that I want to make here is that the chemistry of this fresh water may be a little bit different than the chemistry of this fresh water. So it's a very complicated to try and figure out what's happening in the surface dynamics where those larvae live. And lastly is fresh water, it's buoyant and it's stable when it gets in the Gulf of Maine. It can heat up faster, has a different chemistry, a different Ravel factor, takes less CO2, for example, to change the pH. So there's a variety of reasons we need to be interested in that fresh water. Okay, the other, the last point that I want to make about the Gulf of Maine, the coastal Gulf of Maine being sensitive to OA, is it's got these seasonal mixed layer dynamics that are very important. This is not unusual to many coastal systems, and indeed this diagram comes from Bozak et al., and it's based on the great work that Helmuth used to do, or still does, in the North Sea here. And so what this shows, one of the points I want to make here, this is a two-box model where we have the top box being perturbed in terms of carbonate system by the high productivity. Let me see here. In the growing season here, we have a lot of uptake by algae. Of course, some of this will sink, a lot of this will sink, and start to remineralize back into CO2. So we get this strong gradient. And both these boxes will interact with the atmosphere over an annual time scale, and that might be a little bit different here for the Gulf of Maine and some coastal regions here. So during the growing season, we have this box, these two boxes here. This top mixed layer box will get very, very thin in the summertime. So really thin, and we have a high CO2 pool right underneath that, and so some can diffuse in. If we work that mixed layer down, then it can entrain some of this CO2. So it's quite sensitive to these mixed layer dynamics. In the mixing season that starts around October and continues, then we entrain a lot of this high CO2. So this contributes to the seasonal cycle of CO2 and all carbonate parameters. Okay, so the rest of this talk, I'm going to use some data here. I had hoped to show all these time series assets, but I realized you can't do everything in a 30-minute talk. So all these dots are places where we've had time series. This red series of dots here is a cross-shelf transect originating from Portsmouth, goes out to Wilkinson Basin, and Rue was part of the crew here when we started this back in 2004. So I want to show a little bit on that, and then the main star of the show for us is this UNH Veracruz PMEL CO2 buoy that's been operating since 2006 and started by Doug Vandermark at UNH. And there's other time series here that we've had as well that tell really interesting stories. I'll also show one slide from the Stellwagen Bank benthic OA observatory where we've had deployments over the last couple of years. Okay, so first of all, I plot up this monthly climatology of PCO2 along that Wilkinson Basin cruise track. And so what we have here is time here. And on this axis here, this is Portsmouth Harbor, the minus 70.7, or outside of Portsmouth Harbor. And it goes out to Wilkinson Basin. And this cruise track on the vertical is about 75 kilometers. Here's where we have the buoy right here at this line. So that's along the cruise track here. And you can see if you were taking measurements at the buoy, it would be relatively high in the winter. And then we'd have this tremendous uptake of carbon dioxide that would lower, lower the PCO2. It raises the pH quite a bit. That's great for shellfish. There's typically a lot of food around at that time as well. And then we move along, and it moves up a little bit in August. We have this tendency to have a peak in August, and then it mixes down, and we get the higher CO2. And you see this cross-shelf gradient. So the coast is different. This might be different for shellfish. The coast is different than just 75 kilometers offshore. Okay. The time series also enables us to measure surface variables. And in the red here, we have a seasonal cycle of temperature, up and down, up and down, up in the summer, down in the winter. But we also have this seasonal cycle of salinity. We have quite a range in salinity, between about 26 or so and about 30, 32 and a half here at the surface. And in the middle panel here is our carbon dioxide. You can see there's quite a seasonal cycle there. The black is the in-water carbon dioxide, and the red is the atmospheric. And what we've also tried to do here for this work is to estimate a daily mixed layer, because we think that's really important to try and model these carbonate system dynamics. And the way we've done this is we've taken all our cruise data. Every time we have a cruise near the buoy, that's a triangle here on the bottom, so we have lots and lots of cruises. And then we have measurements at the surface and at 2 meters, and then in the nearby Near-Cruise B buoy, which is only less than 20 kilometers away, we have data at 20 meters and 50 meters, and then we throw that all into an interpolation program, and we get a salinity and temperature profiles to estimate the density, and then we run a program that estimates the mixed layer depth. So that's kind of a long-winded way of saying that we try and estimate this mixed layer depth with these daily estimates of density. And you can see that every spring into summer we have this really, really buoyant fresh layer, and of course that's heating up in the summer, so it's really stable. The mixed layer is super thin. Okay, so on to the actual presentation. That was the background, and now the presentation. I can see that here's the first slide that's screwed up. It should have had the Greek symbol here. But we get asked a lot, or I get asked several times, is there a trend in the carbon dioxide? You see it. We've been measuring it since 2006, and it's a really difficult question to ask. And I usually say there's so much variability attributable to interannual type of variability and annual type of variability that it's hard to deconvolve that. So I've tried for this talk. So what we see is the raw XCO2 data. That's for folks that don't know, it's very similar to PCO2. And I've put a harmonic curve onto that to capture the seasonal cycle. We've also estimated this aragonite saturation index. The Greek symbol here is missing. And before I go on to and so I'm going to show you the residual from this analysis to look at the trends on the longer term. By the way, I just wanted to point out that this is at 1.6 index here, and you can see that routinely, particularly in the fall and of course into the winter, we go lower than this this optimal index of calcification. Okay, so on this slide we show the residual, and again, please realize this is preliminary results, and so there is a trend in the last statistically significant. Rue and I were talking about this a little bit earlier, and we need to apply some decorrelation analyses in addition to taking the harmonic curve out. But the slope won't change even after we do that. And this is this trend in our carbon dioxide is plus 1.25 parts per million per year. So Mauna Loa during this time was plus 2.2 parts per million per year during this time. So we'd expect that with this, now we're seeing ocean acidification here, and omega should start going down. But strangely enough, we have the omega aragonite going up, and going up quite significantly. By the way, the error on that top estimate there is plus or minus 0.34 parts per million on the slope. And this one, omega aragonite, the error is plus or minus 0.001. So it's fairly significant. And what we think has gone on here is there's been a well-documented increase in temperature over the last 8 or 10 years. And this is really driving this particular analysis here. And, it makes me realize that, temperature variability, particularly close to shore when you have strong continental effects, is, it's a multiple stressor or de-stressor that we really need to be mindful of. So in this case, any kind of increase in CO2 has been totally buffered by the temperature increase. Okay, shorter-term variability in PCO2 and omega. Is this relevant, the shorter term, not this longer term that might occur on decades to centuries, but this shorter-term variability? Is it relevant in terms of an organism's life history, and then what causes it? Okay, so as an example of why this may be relevant, this shorter-term variability, I invoked this data set, and my collaborators are Doug, Cindy Pilskin, our student Taz, Ben Cowie-Haskell, and Leela Hatch from the Stellwagen Bank National Marine Reserve. And we've had PCO2 and pH sensors down on the bottom the last 2 years. We've had one 6-month deployment and then one 9-month deployment. This is the 6-month deployment from 2012. And in the red line here, we have the CO2 buoy data, and we can see we're tooling along here at the surface, and then we get this dramatic uptake of CO2, and PCO2 goes down around 200. That was a particularly strong uptake here. And just exactly the same time that the surface starts to go down, the benthic observatory, this by the way is at 93 meters this year. Last year it was at 85 meters. The benthic observatory PCO2 started going up, up, up. And of course we think that these systems are coupled. These two systems are about 60 or 70 kilometers away, but the blue curve is downstream of the buoy's red curve. And so we think that these systems are tightly coupled in time, and that we have a remineralization occurring at pretty tight time scales. And we're analyzing the oxygen and the other data right now to see if that is true on both these deployments. But my point is, if you were an organism that hatched out and ended up in the water column when things started to heat up a little bit, okay, and so this would be, May, plenty of food around, conditions are thermodynamically favorable. And if you drifted downstream in 3 or 4 weeks and ended up in the bottom of Stellwagen Bank, you would experience a change in PCO2 of 400 microatmospheres in less than a month. And so let me put this in perspective with our atmospheric CO2 increase on this line here. We have ice core data for the last 1,000 years or so, and in this darker blue we have recent observations, and then these various IPCC scenario models that go up to 700 or close to 1,000 by the year 2100. Okay, so if you're an organism in the Gulf of Maine, and went from the surface towards the bottom, you're going to experience this range of CO2 right here, and that's well over 100 years of acidification from increasing PCO2. So I would argue that we really need to know more about, what does an organism experience right now? I mean, what is the range of omega and PCO2? Okay, so motivated by these these dynamics that we routinely have been observing in the last decade, and also to try and better understand what the different components are that are perturbing the carbonate system. I've been working on putting these data in the context of a 1D model for the last year and a half, and I'm still not done to the point where I can publish. But I've had some insights, and Doug and Chris are helping me on this as well. And so basically what I'm trying to do is understand this change in PCO2 and carbonate system dynamics at a really short time scale, and then I can scale that up into looking at variabilities over different time scales. But we observe this, and then we try and understand all this other stuff, and it's wicked hard to do this. So the model that I've been using keeps track of changes induced by changes in solubility. And keep in mind these units are in change in PCO2 per day. When we can model that very effectively. And same with the air-sea flux. We have plenty of data to model what the flux of carbon dioxide that comes into the mixed layer or goes out of the mixed layer, and it changes the concentration and partial pressure of that carbon dioxide. So it's a slightly different perspective there. We can model that quite effectively. We also try to model the change in PCO2 attributable to horizontal mixing, and that's a fairly big error term, but we have a way moving forward to do that with some assumptions, and we've done a pretty good job of that. And then also this change from net vertical mixing, and that is a function of the change in mixed layer depth and also diffusion. And the diffusion can be quite an important process. I missed that part of Helmut's talk because I was at a meeting. But I would agree that diffusion, particularly vertical diffusion, is very important, particularly when the mixed layer is very thin. And then the residual of this whole mess is what I'm calling NCP star, which is the sum of the biological processes, the autotrophy, heterotrophy, and calcification. Okay, so on to results from this. It doesn't, these plots of very high frequency daily variability. Now keep in mind that this is the change during a day plotted per day. This is our observed right here, and this is our air-sea flux. And I don't expect you to be able to see that very well, but the point is that the change in the PCO2 in the mixed layer just from air-sea flux can be over 4 microatmospheres per day. Okay, the changes in solubility invoke a change in PCO2 of up to 3 microatmospheres per day. So this is the change that's largely attributable to the heating and cooling cycle, but also from the salinity cycle. And that's an underappreciated factor, that changes in salinity in the coast have a dramatic effect on the solubility. And a lot of people don't even model that out, but I'm here to say that I think it's important. Okay, more results. This is a vertical processes, and of course you can see this curve when we have, it's all these positives, so there's all these CO2 fluxing from the deeper into the mixed layer. But you can see where these storms occur, and when we're starting to mix down and deepening the mixed layer here, we can have, actually we can have like 10 microatmospheres per day, and I'll show some results from that. And then horizontal mixing as well, we can have fairly dramatic time periods in which the freshwater horizontal flux is affecting the daily PCO2, and this whole residual of net biological processes tends to follow a seasonal cycle, of course. Okay, so let me give you, again, that didn't lend itself very well to a webinar, but let me show you one example of where this daily modeling may be of use of trying to understand, perturbations to PCO2 in the carbonate system. Okay, so here's one short-term example of a change during a storm. And so what I have here in the red line is the density. And in the black curve on the top panel here is the wave field. And these are from the Neracruz buoy B data. And these are really high frequency. I think 15 minutes or half hour at the most. And what we see here is a storm approaches, and the waves build up, and they persist. They persist for this is a couple-week time period right here. And as these waves beat down the mixed layer, you can see the density rising. And so here, down on this lower curve here, we have this density, same density plot right here. And now it's on the those units are on the left-hand side. And here we have the observed delta PCO2, the difference in PCO2 between the atmosphere and the water. And you can see, and this is modeled daily. We measure it much more frequently, but this whole model runs on a daily time step. And you can see this increase of 70 microatmospheres in 12 days. That's a very significant increase. It's similar to the productivity that occurs in a week or so in the springtime. Okay, and so what we've done here is, so again, I'm going to show you the actual model results here, is here is the same panel with the density going up and the delta CO2 going up. And so, what our model does here is detects a change in the deepening of the mix layer there, and it starts to mix these deeper pools of carbon dioxide. It's really TIC and TA, but for this audience, I'm going to keep on using carbon dioxide. And over the storm, and it causes the delta PCO2 to go up. So we have this split with a storm, and if we accumulate these modeled results, it shows the PCO2 going up 60 microatmospheres versus 70. And I want to point out, we would completely miss this with, with just measuring the PCO2. We completely miss this if anybody's, going on 4 cruises a year or, even monthly cruises a year. We don't go out during these storms. So we've got to work toward, and I may not be the best person to do this, but we've got to work towards modeling this system, because I think these high-frequency changes are quite important. Okay, so on to accumulating these results to try and make sense of a seasonal cycle here. And so, as an example, I'm going to show these results in the same units, the change in PCO2 over the day, but now I'm taking and I'm accumulating those results over a climatological year. And if that doesn't make sense, hang on a second. So if you can imagine that we take a parcel of water here in January and we heat it up over the course of the year and then let it cool down over the latter half of the year, this would be the ride that the parcel of water would take just from the changes in solubility over the course of the year. So this would change 250 microatmospheres just from this heating and cooling and changes in salinity. Okay? And so now I've done the same thing with our actual observed data here in this black curve down here. So we accumulate the climatological observed data over the year. We see this big drawdown of carbon dioxide that works itself back up towards August, goes back down again, and then works itself. So these are our actual results from the observations. And so the difference between these two curves is this dashed line with the X's in it here. Okay, so this is attributable to the mixing, both horizontal and vertical, the entrainment the air sea flux and the net biology. Okay, and so interestingly, you could say, okay, well, biology, but you wouldn't think that it would keep going down here in the, in July, and even, yeah, it goes down a little bit between July and August, and that really confuses us. Okay, and so when we actually apply the model, we have a very different perspective of what's causing this residual line right here. So on the right-hand panel now, we see this exact same curve in the red here where we have this solubility raising the carbon dioxide and lowering the carbon dioxide. And this black curve now is the same observed. This is what we actually observed. Okay, but now we've calculated the air-sea flux, and that's the dashed line with the circles on it right here. And this follows a seasonal cycle where that, when the biology is present, drawing down the CO2, that the flux of carbon dioxide goes in, and vice versa when things are respiring or mixing. But this is a very, very big term, the air-sea flux. And another large term, and these are typically positive here, is this entrainment term. It's usually quite small on the daily basis, but it accumulates, and it keeps accumulating, and it's always positive. And when the mixed layer gets really thin, you can see the inflection of this curve goes up a little bit, and then when we entrain, the inflection goes up again. So we have to consider this diffusion and mixing down. And then lastly, the horizontal flux. When we get these fluxes of fresh water from the local rivers or from the Scotian shelf, it has a tendency to lower the change in PCO2 per day. And this shows a seasonal cycle here, pretty much. So the error terms, by the way, in this blue curve and in this yellow curve are very large, 50%, in some cases 100%. But we think we've captured at least the effects of them. Okay, and so I guess this concludes my presentation. But it's clear that in the Gulf of Maine, there's action from several significant processes at several time scales. And the daily, the weekly is important, the seasonal, the decadal, and of course the climate. There's changes in solubility, acid flux, mixing. Freshwater flux. Keep in mind that climate change can change any one of these. It's not just the increased PCO2, especially near the coast. And so it's really important to try and understand what's going on, in my opinion. And the unresolved issues that we have in our carbon group at the UNH is one, we really haven't done a good job of trying to understand the natural variability in the carbonate system in the Gulf of Maine. Even though we're treating organisms in labs and we're saying that, okay, this is the way it's going to be at 2050 or 2100, we've got to go back and look at these observations. Short-term events are really important. Floods, storms, productivity, they really affect the PCO2 and the omega. And it might be that, some organisms take advantage of this, not just the food availability, but the thermodynamics of the uptake of CO2 to build their shells. And the effects of circulation and freshwater sourcing are very important in change at all kinds of different timescales, interannually, decadal. And what the heck is going on with this NCP in the early summer, in June, and sometimes even in July? There shouldn't be nutrients around to continue to perturb the carbonate system, but there seems to be in all our data sets, and I know the Helmuth and Elizabeth up to our northeast have seen this as well. So that's it, and I'll turn it back over to Ruth.